have Bill Bell, also from the U.S. Census Bureau, and he is presenting Modeling Weather Effects and Seasonal Noise in U.S. Monthly Regional Housing Starts. Bill, you can go ahead and get started when you're ready. Bill, you're on mute if you've started.
Sorry about that.
No problem.
Thank you, Becca. There. Let's see. So this is a talk. At least much of it has been given before, and the whole thing recently internally, but not in this forum. And as I say, some parts of it were given before, but I have some new results. It's joint work with Osbert Pang of Census, and also Brian Monsell when he was at Census, and Thomas Trimber. We collaborated and work on this. There's a couple background references. One, a paper by Thomas and I on seasonal noise modeling, and then Osbert and I and Brian have a tech report on modeling explicit weather effects. So here's graphs of time series of U.S. regional housing starts that go back all the way to was 59 or 60, and we stopped using the data at the end of 2019 because we didn't want to deal with pandemic effects for the analyses. So anyway, and it's for 4 regions of the U.S. Here's for the Midwest and the West regions. You can see strong seasonality. The peaks and housing starts are in the summer. The big dips are in the winter. It's for the Northeast and South regions. And here's shorter segments of it for the sort of the most recent 20 years. One thing to note is here in the Northeast, there's this big outlier, which had to do with a change in regulations on, I think, building permits in New York City that led contractors to try to get their projects started before the date that these regulations went into effect. And so we accommodate that with an additive outlier term. Here's a map of the 4 regions of the U.S. And one of the things about looking for weather effects is that for a geographically large country like the U.S., weather is a rather nebulous concept. Even within a region, there can be great variations in weather over a given month. So trying to track the effects of weather that is, not so focused on regional housing starts can be a bit of a challenge. And here's some graphs showing what sort of got me thinking about this years ago. I had noticed in modeling housing starts and also building permit series that the outlier detection was coming up with outliers that were almost all in the winter months, January and February primarily. And so here are box plots of additive outlier T statistics by month for the 4 regions. And you will notice that for the Midwest and the Northeast in particular, the variability in January and February and December is substantially larger than it is for the rest of the months, predominantly. and with outliers showing up, particularly in January and February. This is much less true for the West and the South regions, which do not suffer from the severe winter weather, at least in the key population centers, nearly as much as the Midwest and the Northeast regions. So there's sort of two general questions here. One is, to what extent can this higher variability and potential outliers that occur particularly in the winter months be explained by time series models as due to severe weather effects by incorporating weather data into the models? And secondly, how would modeling and possibly adjusting for weather effects affect seasonal adjustments? And here we'll focus on results for the Midwest and the Northeast regions. Now, others have worked on this before. Here's some references taken from real estate journals. And these authors have approached the problem. I mean, basically, it's the same game that everyone has to play. You collect weather data for a lot of sites within the regions. You then create regional weather variables out of that data, and then you stick those in models and see if you can explain away significant variation with the weather variables. And the general conclusions from this was evidence of effects of unseasonal weather, especially in winter and for the colder regions. And the authors used different modeling approaches, but the general conclusion sort of held up. We think we've cleaned up the modeling a little bit. Osbert found other references that were studying weather effects on other time series. So it's not just for housing construction, although that's an obvious choice. I won't go into them. So I want to briefly review some modeling of weather effects. It's covered in this tech report that Osbert and I and Brian have. That involves creating weather variables for the regions and trying to explain weather variation that way. So we have a Regorima model where the dependent variable is log of housing starts over length of month. And this X here contains trading day variables, which aren't terribly important in these series, but sort of marginally significant, so we put them in, along with regional weather regressors. And then we got this additive outlier for this outlier in the Northeast. And the question is, how important are the regional weather regressors? And the airline model works pretty well for these, for the regression residuals. So here's, I'm going to summarize what Osbert did in putting together these regional weather variables. So weather data is readily available for the US from something called the National Climatic Data Center. And so he collected these data, and the format of the data changed in recent years. So now you can get daily data. But anyway, he was looking at monthly summaries of weather measures in three categories: temperature, precipitation, and snowfall. And so you can see we got variables here reflecting cold temperatures. This is, below 0 Fahrenheit or below freezing. Here's for hot temperatures and min and max values. And these reflect amounts of rainfall. And when you put these in models, these variables, some of them are highly related, like the different cold temperature variables. So it isn't necessarily that crucial which one you pick. The question is more, how important are, these things generally with one or more of these variables. And the way this is done is you can get weather data for various monitoring sites like airports, and taking collections of those measurements over a month to put them together into a monthly summary for a region, one problem Osbert had to deal with was missing values. So he did some interpolation for those. And the other is how do you put together the measurements across many sites in a region? And I don't have time to go into that here. That's a problem, you know, that anyone would have to do in this kind of modeling. But one thing to do is to weight the measurements by population. So you've got several sites in a metro area. Take the population of the city or the metro area and somehow weight your measurements up by that and then aggregate over the region. So as I say, I don't have time to go into that. That's an important step. And that's what produced the weather variables that we considered. So I'm going to jump to the results, summarizing some results that Osbert got, because he fit models with one weather variable, models with two weather variables, and so on. And he seemed to get pretty good fits with 3 or 4 variable models. And here are the 3 variable models that fit the best. And we see for the Midwest here, we've got this cold temperature variable, and we've got snow depth, and we've got a precipitation variable. So it didn't have to come out this way. But if you do a 3 variable model, it's good to have one that turns out from each of the 3 categories. And you can see T statistics on the coefficients of these show that they were highly statistically significant. Northeast has similar results. The first 2 variables selected are the same as for the Midwest. The third is a precipitation variable that's total precipitation. And interestingly, the snow depth wasn't significant, but it did enter an AIC-based model selection, so we retain it. The question was whether including these weather effects variables in models could explain away what were showing up as additive outliers before. And here are results on this for the Midwest and the Northeast. So for the Midwest, a model without any of the weather effect variables turned up 9 additive outliers in the months shown. And when the weather effects variables on the previous slide were included in the models, 5 of these AOs disappeared. So the weather effects variables could explain some of the outliers, not all of them. And for the Northeast, we got similar results. Without, there were 7 additive outliers, and with the weather effects variables in the models, that eliminated 4 of them. So the general conclusion is that the weather variables can explain some outliers, but not all of them. So now I'm going to discuss some work of mine done previously and with Tom Trimber on modeling seasonal noise or seasonal heteroscedasticity, using the terms interchangeably. And to do that, we used a reg component model where, you know, we started with the same kind of thing as before, although without weather regressors in the X's. We have trading day here and an airline model for Z. And then we have these noise terms, multiple noise terms, potentially 1 for every month. So epsilon I is a noise term, and HIT, which are the scale factors that I mentioned for that we have in the reg component program, those are month indicators. So H1 is 1 in January and 0 otherwise, and it picks out this noise term, which has its own variance, and so on. So if we have the full set of months in here, we've got 12 of these. But it may be that we don't need seasonal noise in all the months, and so script S here could be a subset of the integers 1 to 12. And I had an algorithm to determine how many of the months to include. I won't go into that for lack of time. But let me show you model comparisons using AIC and BIC with different number of months included in the models with seasonal noise. So in the upper left here, the 0 on the x-axis indicates no weather variables in the model. And this is the AIC difference of that model from the lowest in this family, which turns out to be out here at the end with all 12 months having seasonal noise in the model. So we see what happens is that when January is added to the model as having seasonal noise, the AIC drops precipitously by like 80. So that's a big difference. So January seasonal noise is clearly important. The next most important is February. You get another big drop in the AIC. December produces a substantial drop in AIC. And after that, there's really not so much, and things even climb up a little bit out here. So January, February, and December are the big months for seasonal noise. If you use BIC, because it has a heavier penalty on adding parameters, the AICs drop down to December being added, and then they start going up. So again, January, February, and December are the key months. For the Northeast, it's similar, except that December is not as important. So we get the big drops in January, February, less in December, and then not much after that. And BIC doesn't like putting in anything beyond December. So in what follows, I'm using January, February, and December as the months with seasonal noise. So that's interesting. Okay, so that's interesting. We found that the weather effect variables can explain significant variation in these series. We found seasonal noise is important in the models. But one question is, do we need both of these, or can we get by with one and not the other? And the other is, how does modeling and possibly adjusting for the weather effects affect resulting seasonal adjustments and trend estimates? So here I will jump to AIC and BIC comparisons of the models with and without the 3 months with seasonal noise, or with and without the weather effects that we had previously and the seasonal noise for the January, February, and December. And so the first line would be for the model without either of these, and the table is showing differences from that model, so they don't have an entry. When we add the weather effect variables, AIC and BIC drop substantially, so clearly those are very important. If we don't have the weather variables but add the seasonal noise, again, compared to having neither, the AICs and BICs drop a lot. And if we put them both in, then they drop even further. So in answer to question 1, yes, we need both the weather effects and the seasonal noise in the models. So now let's look at how adjustments for weather effects compare to seasonal adjustments without weather effects. So this is for the Midwest and showing basically the last 20 years. So, we can discern the graphs. So this upper left graph compares X11 seasonal adjustments in red with airline model-based adjustments, a la seats, in green. And we can see that the adjusted series are similar. You can see the green appearing from the red, though maybe not drastically different. And in the remaining 3 graphs, the green curve is the same as it is in the upper left. It's the airline model-based adjustments. In the upper right here, I compare that to an adjustment from the reg component model with the airline model plus the seasonal noise, this is with the weather effects put into the model, and we adjust out the weather effects. So here we see that the blue curve, which shows the adjustments both for the seasonality and the weather effects, is substantially different from the green curve by more than we see the X11 adjustments were in the upper left. The lower left shows the adjustments for seasonal noise without the explicit weather effects. And the blue curve, which includes the seasonal noise adjustments, also shows substantial differences from the model without the seasonal noise. And if we put both the weather effects and seasonal noise in, we again see big differences in the adjustments. Here's the ratios of the adjustment factors corresponding to the previous four graphs. So here's the ratio of the X11 seasonal factors to the airline model-based seasonal factors, and we see differences. Interestingly, there's a kind of a bias here, which is reflecting a difference between the airline model-based as a log additive seasonal adjustment and X11's multiplicative. So there's more to be studied there. That kind of bias shows up once in a while, but I won't dwell on that here. Here in the upper right are the ratio of the airline model-based seasonal factors and the adjustment factors from the airline model plus seasonal noise. And here we see, substantial differences from 1 in these ratios, by far more than the comparison of the X11 and airline model seasonal factors. Now we've got 30% up or down differences in the factors. Here's the comparison with seasonal noise. These are even some larger differences in the adjustment factors. And here we have the model with both. So that's for the Midwest. I'll just briefly show for the Northeast, we get sort of similar results. X11 versus airline model-based adjustments. You can see some differences there. They aren't very big. Much larger differences when we bring in the adjustments for weather effects or seasonal noise or both. And here are the ratios for the adjustment factors, again, reflecting the importance of the weather adjustments or the seasonal noise adjustments. So conclusions are we found that both the explicitly modeled weather effects and the heteroscedastic seasonal noise were very significant for modeling the Midwest and Northeast housing starts. The weather effects could explain some, but not all outliers. And the seasonal noise reflected a larger amount of variation than the modeled weather effects, especially for the Midwest. So question 2, should we adjust for weather effects or seasonal noise? And I think it depends in principle on the objectives of the data users. Some people may want to see, what the adjusted series would have looked like if not for unusual weather. Others may want to see it reflecting the unusual weather. So it's not like there's one right answer for this, I think. For seasonal noise, I think it's a little trickier. If you're doing trend estimation, I think it's clear we'd want to adjust out seasonal noise. For seasonal adjustment, whether we also want to take out the seasonal noise, I think is not as clear. But in any case, the examples have illustrated that adjusting for weather effects and seasonal noise can have substantial effects, and that in the example, they were, far more consequential than making a choice between X11 and airline model-based seasonal adjustment.
Okay, great. Thank you, Bill. This was a really interesting presentation, including weather. Does anyone have any questions? We have time for a question or two. I think it was really clear. I would be interested in how you compiled the different variables, but I know you said that's not covered in this talk. But
yeah, that is in the research report in detail.
Awesome. Okay, well, if you have any questions, please feel free to put them in the chat. We'll move on to the next one.